Hi, folks. Today we're going to talk about combinatorics. Now, combinatorics, it's a very complicated one. It starts with very simple ideas, but it can get so complicated so quickly. And so I'll do my best to explore some of these topics with you. But if you want to do a deep dive into combinatorics, you might be looking at a probability and statistics course in your future. And so what is combinatorics? Well, the field of combinatorics is the study of counting principles. It begins with the idea of counting combinations of things. And so how do we count? Um, but quickly it builds around the idea of measure theory with applications to a wide variety of fields. Probability as a field of study is built around the structures of combinatorics. You can't really do probabilities without combinatorics. In fact, when we think about what probability is all about measuring uncertainty. Well, in measuring, we need the measure theory. Combinatorics is an approach to measure theory which uses discrete math. And so this is kind of like the stuff behind the scenes for all of the probability work. And so we're going to learn some of the basics. We're going to start with the foundations, and then we're going to focus on some formulas. The formulas can get a little bit messy, and you can see a couple of the formulas popping up here already. We'll do our best to explain them, but again, to master combinatorics, you need combinatorics course. And so introductory problems that demonstrate a need for counting. Our first one is the idea of a complete graph. And so a complete graph is a graph with the property that every vertex is directly connected to every other vertex via a single edge. How many total edges are there for n vertices? And so in this case, we can see that we have 7 total vertices. Well, if we wanted to, we could count them all out. And so one approach, if we're just thinking broadly, each node is connected to 6 other nodes, right? If you look at this one, 1, 2, 3, 4, 5, 6. This one is also connected to 6. This one's connected to 6. Since we have 7 of them and each one is connected to 6, our initial thought might be 42. But we would quickly remember that we would be double counting, because if we think of all of the nodes or all of the edges which are connected to this vertex, well, this edge would be counted for this one and for this one. And so we'd have to divide by 2. And so this gives us a way of understanding how we can count this. We could also just go one at a time and see how many we have at each one. And so like for this one, we have 6, which we would be looking at. But as soon as we go to 2, well, one of them's already done, so we only have 5 new ones. At 3, well, we would have 4 new ones. At 4, we would have 3 new ones, then 2 new ones, and then 1 new one. And so this math is the same as adding 6 plus 5 plus 4 plus 3 plus 2 plus 1. What we've just proven is that if we add up all of the numbers from 1 to n minus 1, we're going to get n times n minus 1 over 2. When I say prove it, I mean we just give an example of it. We could prove this if we wanted to. Gauss did. Another guiding example is the chessboard problem. And so suppose that you have a chessboard, such as the one to the right, which has 2 squares removed from opposite corners. And so we've removed this white square and this white square. There are now 62 squares left. So suppose that you have 31 dominoes, where each domino is covering 2 adjacent squares. They could be adjacent horizontal or vertical, but not diagonal. Is it possible to cover the 62 squares using the 31 dominoes? And it is not. The reason is we can actually think of a domino as covering 1 white and 1 black square. And when we count how many squares we have, we'll notice we have 30 white squares, but 32 black squares. That presents an issue. If each domino only covers 1 black square and there are 32 black squares, we would need 32 dominoes. 31 would not be enough. Another old school topic is the idea of magic squares. And so magic squares are puzzles developed in China, Japan, and India, which are pretty easy to understand and analyze. And so suppose that you have the numbers 1 through n squared, with n being something greater than 2. Can you place the numbers in an n by n grid such that the sum of all rows, columns, and the two main diagonals all add up to the same numbers? It turns out you can. There are many computations and analyses that can be done with magic squares. For instance, given n by n numbers, the sum of all of the boxes is given by 1 plus 2 plus all the way out to n squared, which we can prove is n squared times n squared plus 1 over 2. And then the sum of each row would be this thing divided by the number of rows, which is n. So all of the rows must add up to give you n times n squared plus 1 over 2. We also have the idea of reflections and rotational symmetries. If you rotate or flip a magic square, you get a new magic square. And magic squares are not uniquely structured. If you look here, we have two 4x4 magic squares, and they are different. They're very, very different from one another. And so the question becomes, what makes them different? And are there other versions? And so in all three of these examples, we have some understanding of counting combinations of things. And it really depends on the types of things we're counting. It's not always immediately clear how to count things, or how to organize information, or how to solve problems using those types of counting techniques. The counting techniques of combinatorics gives us the tools to think through counting in a more general way. And so let's talk about the fundamental properties, and then we'll go into some of the scarier looking formulas. The fundamental properties, these are fairly nice. And so our first one is the addition property. Suppose that we have n distinct sets, S1 through Sn, which have no common elements. We say the order of each set is the number of elements in each set. Then the order of the union of these sets can be determined just by adding the number, or adding the order of each set. This is one of the most fundamental properties of counting. When counting groups of things, we can count up the number in each group and add them together. And so here's our old school example of goldfish. How many goldfish do you see? Count how many goldfish in each fish tank and add all the numbers together to find the sum. If you'd like, give it a shot. I didn't write out the answer, and I'm not willing to count the goldfish. And so I trust your answer is correct. Good job. The next one is bags of marbles. And so suppose that we have two bags of marbles. The first one, or the first bag, is going to have 3 marbles, numbered 1, 2, and 3. The second bag has 4 marbles, numbered 4, 5, 6, and 7. If you combine the 2 bags of marbles, how many total marbles would you have? Well, that's the addition property. Do not overthink it. You will have 7 total marbles. Well done. The second question, though, is a little bit more interesting. And so if you select 1 marble from each bag, how many different combinations of marbles could you end up with? Well, that's a little bit more complicated. And so let's focus on this second question. If we think of this problem in set notation, we are dealing with the Cartesian product of sets. And so let S1 be equal to 1, 2, 3, and let S2 be 4, 5, 6, and 7. Then this combination could be represented as the ordered pairs between them. And so we'd have 1 and 4, 1 and 5, 1 and 6, 1 and 7, 2 and 4, 2 and 5, 2 and 6, 2 and 7, 3 and 4, 3 and 5, 3 and 6, 3 and 7. In total, we have 12 possible combinations. And so the first set had 3, the second set had 4. How do you get from a 3 and a 4 to a 12? This is our multiplication property. And so suppose that you have 2 distinct sets, S1 with P elements and S2 with Q elements. The Cartesian product, S1 cross S2, is a new set which consists of all ordered pairs with first values from S1 and second values from S2. The set will have P times Q elements in it. What this means is that if we are looking for how many combinations there are from selecting items from two distinct sets, we can just multiply the number of elements and we're done. This works for more than two as well. And so if you have 12 distinct sets, just multiply the order of each set together and you're done. Let's try a practice problem. Suppose you have 4 bags of marbles, each with 3 marbles, and we're going to label them all A through L. And so bag 1 has A, B, and C, bag 2 has D, E, and F, then G, H, and I, then J, K, and L. I am so glad I didn't mess up my letters. Suppose you select 1 marble from each of the 3 bags. How many different possible combinations are there? Well, we have 3 marbles in each bag and 4 bags. And so we are going to have 3 times 3 times 3 times 3, which is 81 total combinations. Another thing we need to consider when we're talking about this is the idea of order and repetition. And so when counting objects, we often consider if the order matters and if repetition matters. A selection is ordered if we care about when things are selected, and they are unordered if we do not care about the order. And so, example, in an ordered set, 1, 2, and 2, 1 would be considered 2 different selections. But in an unordered set, they would be considered the exact same selection. A selection allows repetition if we can get the same value a second time. A selection is without repetition if we can get the same value twice. If we cannot get the same value twice. I was like, that didn't sound right. And so in the marbles example, suppose we select a green marble from the bag. If we allow repetition, that means we are putting the green marble back in and selecting a second marble. If we do not allow repetition, we do not put the green marble back into the bag. With this, let's do 4 examples to show how weird things can get. And so marble from a bag, twice. Suppose we have a bag with 4 marbles numbered 1 through 4. If we select 1 marble, put it back in the bag, and then select a second marble, how many different possible combinations will there be, assuming that the order matters? And so in this case, it's order matters and with repetition. Well, in this case, we can use the multiplication property. And so because the marble is reintroduced to the bag, the problem is no different than choosing a marble from 2 different bags. As such, there are 4 times 4, so 16 total combinations. If we listed them out, we would get 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. And so 16 total combinations. And so this was order matters with repetition. Now let's try it where order doesn't matter, but we still have repetition. So suppose that we have a bag with 4 marbles numbered 1 through 4. If we select 1 marble, put it back in the bag, and then select a second marble, how many different possible combinations will there be, assuming the order doesn't matter? Well, if we assume order doesn't matter, we can still begin with the 16 possibilities from before, but repeated pairs, such as 1, 2, and 2, 1, would only count for a single value. And so there are 6 such pairs. Removing the repeated values, we are left with 10 total combinations. And so looking at this, we have 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, and 4, 4. We've seen this type of pattern before. And so note that the starting values of these pairs, the 10 values could also be calculated as 4 plus 3 plus 2 plus 1. This is the same as the graph example that we had. And so now, suppose that we have a bag with 4 marbles numbered 1 through 4, and we're going to say order matters without repetition. And so if we select 1 marble, put it to the side, and then select a second marble, how many different possible combinations will there be, assuming the order matters? So in this case, from the 16 combinations, we can remove the 4 repeated values, leaving 12 total combinations. We're not getting 1, 1, we're not getting 2, 2, we're not getting 3, 3, we're not getting 4, 4. Everything else is still fair game. Another way to calculate this, initially, when you grab a marble, there are 4 marbles to choose from. But after you've removed 1 marble, there's only 3 left to choose from. And so this gives us 4 times 3, which is our 12. If we want, here they are listed out. 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. And one final manipulation of this problem, this time order doesn't matter and without repetition. And so if we select 1 marble, put it to the side, and then select a second marble, how many different possible combinations will there be, assuming the order doesn't matter? And so this is the same as the previous example, but now the order doesn't matter, meaning a 1, 2 and a 2, 1 would only count as a single combination. Since each of the 12 combinations before is repeated, we have to divide by 2. And so we get 6 total combinations. We could get 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, or 3, 4. Note the starting values of each of these pairs. The 6 values could also be calculated as 3 plus 2 plus 1. Again, that's kind of similar to that complete graph problem we saw before. Here's an advanced problem. And so taking these ideas that we just had and applying the multiplication property, how many odd numbers are there between 1,000 and 9,999, which have distinct digits, meaning none of the digits repeat? Well, we can take each digit separately. And so for the ones place, we know we're talking about odd numbers, and so there are 5 possible digits for the ones place. For the thousands place, there would be 9 possible, because they're going to get 1 through 9. For the tens and 100s place, well, we have 10 possible digits. We get 0 through 9. Because we do not allow repetition, we can start with a more complicated condition and work our way out. And so we start with the idea of 5 options for the first place. And so let's say that we pick one of those options. Well, after that is selected, there can only be 8 options for the thousands place, because 0 is not an option, and whatever we picked first is no longer an option either. After that is selected, well, for the hundreds place, we've already got 2 numbers gone, and so the only option would be 8 different options. And after that, well, now we've got 3 numbers already picked, so there's only 7 options left for the tens place. In total, we can use the multiplication property and say that we've got 5 times 8 times 8 times 7, or 2,240. And so there's 2,240 numbers between 1,000 and 9,999, which have distinct digits. That one's a little trickier. Speaking of trickier, let's get into some of the messiness of combinatorics. Before we do that, let's talk about factorial notation. And so before we go further, let's review what it means to be a factorial. Given a whole number n, we denote n factorial using this exclamation point to be the product of every number from n down to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320. If we did 8 factorial divided by 5 factorial, well, that would just give us 8 times 7 times 6, because we would be getting rid of all of the 5 and down stuff. And then 1 factorial is 1. And then just to be a little bit weird, we're going to say 0 factorial is also 1. There are some calculus reasons as to why this is. There's some measure theory reasons as to why this is. We're not going to go into them. For our purposes, we're just going to assume we're all cool with letting 0 factorial be equal to 1. And with that, we're going to start talking about some of the more complicated formulas that arise. Now, I do not want to get into the weeds when it comes to this stuff. And really, to get good with these different formulas, you need to practice a lot. You would want to spend probably a month or two just focused on all of the different counting principles, because there's a lot of different counting principles. And knowing when to use which one, it can take a lot of practice. And so we'll see if we can focus more on the different types of examples that we see, and we'll show what the different formulas are as we're going through it. And so here, we're going to talk about permutations. And so let R be a positive integer, and suppose you have a set S with n elements. Then the R permutation of a set is the collection of ordered arrangements of the elements of S of length R. Think R marbles chosen out of a bag with n marbles in it. No repetition and order matters. Let's look at this example here. And so, for example, let S be equal to A, B, C. And so this is just the letters A, B, and C. The set of 1 permutations of S would be A, B, or C. And so these are all of the possible things of length 1, where we're not repeating any of the values. The 2 permutations of S would be AB, AC, BA, BC, CA, and CB. And so this is all of the possible combinations of A, B, and C, which are length 2. And then the 3 permutations of S would be ABC, ACB, BAC, BCA, CAB, and CBA. And so this is all of the possible combinations which are of length 3, using those 3 letters. If we wanted to, we could count this up. The permutation 3-1 is going to be 3. Permutation 3-2 is going to be 6, and the permutation 3-3 is going to be 6. We have a formula for this, and it's not a terrible formula. And so suppose that n and r are positive integers with r less than or equal to n. Then this permutation is going to be given by n times n minus 1 all of the way down to n minus 1 or n minus r plus 1. If we want, we can visualize it like this. And so the permutations, the number of possible outcomes, is going to be n factorial over n minus r factorial. And this is sometimes written as NPR. And so here's an example. Suppose we're pulling 3 marbles from a bag with 5 marbles in it. No repetition, and the order matters. The first marble you pull, there are 5 possibilities. The second marble you'll pull, there are 4 possibilities. The third marble you pull, there are only 3 possibilities left. And so in total, we can multiply these together. 5 times 4 times 3 gives 60 possible permutations. Combinations work a little different. And so the R combination of a set is a collection of unordered arrangements of the elements S. And so now when we're thinking about the order doesn't matter. If we see AB, that's the same as BA. And so thinking of that example we did, let S be ABC. The 1 combinations, and so how many ways can we pull one thing out of here? Well, it would be A, B, or C. The 2 combinations of S would be AB, AC, or BC. We wouldn't include BA because BA would be viewed as the same thing as AB. Same with CA, that's the same as AC. And CB would be the same as BC. Because of this, the 3 combinations of S would just be ABC. Any rearrangement of ABC is still ABC when we're talking about combinations. And so counting the elements, our combinations are for 1 element is 3, for 2 elements is 3, and for 3 elements is 1. We have a formula for this. And the formula is actually very similar to the other one. You might have noticed. If we take our permutations and then we just divide by r factorial, this r factorial on the bottom, that's telling us how many times those individual elements were being repeated. And so if we go up a couple spots, here we go. We can see AB and BA, well, they were repeated twice. AC and CA, that was there twice. For the three permutations, well, ABC is repeated 6 times for permutations. And so we would need to divide by 6. And so our combinations is just our permutations divided by r factorial. We see this written sometimes like this, NCR. Sometimes we just see it written like this, NR. Or N choose R if you'd like. Suppose we are pulling 3 marbles from a bag with 5 marbles in it. No repetition, order doesn't matter. And so we previously found that there are 60 different permutations. Since order doesn't matter, each of our combinations is repeated 6 times. That's our r factorial. Dividing by 6, we find that there are 10 possible combinations. And so this is just taking that past example, dividing by how many times they're repeated, and we end up with 10 different combinations. Now we're going to get into some messier stuff. And so permutations with repetitions. Let S be a multiset with objects of k different types with finite repetition, n1 through nk. And let the order of S be the sum of all of these n sub k values. Then the number of permutations of S is equal to P of S is equal to n factorial over n sub 1 factorial, n sub 2 factorial, and the product all the way through n sub k factorial. These are ordered arrangements with repeated values. Now, there's a lot of jargon there. Let's look at this example of Mississippi. How many permutations are there of the letters of the word Mississippi? That means how many different ways can you arrange the letters in the word Mississippi? Well, we have 1 M, we have 4 I's, we have 4 S's, and 2 P's for a total of 11 values. In this case, each of these values, the 1, 4, 4, and 2, that's telling us the order of each of those letters. And so we can think of each one of those as being one of our n sub k values. The 11, well, that's our total n. And so our permutations, the number of permutations, would be 11 factorial divided by 1 factorial times 4 factorial times 4 factorial times 2 factorial. This ends up being a very large number divided by 1,152 for a total of 34,650. That means that there are 34,650 different ways to order the letters of Mississippi. Now, if we'd like to see all 34,650 different ways to order the letters of Mississippi, let me just go to the next slide. And, oh, I forgot to make that slide. Oh, well. So permutations with repetitions. Suppose that we have k different types of objects. If we are allowed to repeat objects as many times as we like, the number of permutations of length r is given by p is equal to k to the r. And so this would be the case where we pull a marble out of a bag, then reintroduce it to the bag and pull it again. Order matters with repetition, but there's no limit on repetitions. And so thinking the Mississippi example again, Mississippi is an 11-letter word consisting of 4 letters, M, I, S, and P. How many 11-letter strings of letters are there with just M, I, S, and P? Well, in this case, we could just say that since we have 4 types of objects and we're looking to for permutations of length 11, we could just take 4 to the 11th power. That's going to give us 4,194,304. I'm sure you all already knew that number though, so don't worry about it. Combinations with multisets. So this is where it gets even weirder. And so suppose that we have k different types of objects. If we are allowed to repeat objects as many times as we like, then the number of combinations of length r is given by this kind of messy formula. I usually think of this one in terms of donuts. And so suppose that a bakery boasts 8 varieties of donuts. If a box of donuts contains 1 dozen, how many different boxes can you buy? Well, in this case, there are 8 types of donuts, and we wish to know how many combinations of length 12 there are. And so using this formula, we're saying that we're going to have 8 plus 12 minus 1, which is going to be 19 factorial, over 12 factorial times 8 minus 1, so 7 factorial. And we end up getting 50,388. That's a very large number. If we'd like, here's a couple practice problems. Suppose you have a bag with 3 green marbles, 2 blue marbles, and 5 red marbles. If you pull them out one at a time, how many different possible orders could there be? Well, this feels kind of like that Mississippi problem. And so for number 2, suppose instead that we introduce the marbles to the bag, or we reintroduce the marbles to the bag after pulling them out each time. How many different orders could there be after pulling 10 marbles? Well, this would be the other side of the Mississippi coin, right? Where we would have 3 different types, and we would end up with 3 to the 10th different options. And so for the first one, this was a permutation with repetition. 3 greens, 2 blues, 5 reds, 10 total. And so we use the Mississippi formula and factorial over n sub 1 factorial, n sub 2 factorial, all the way out. We end up with 2,520. For the second one, it's still a permutation, but in this case, there's no limits on repetition. And so with 3 types of marbles, we get 3 to the 10th, or 59,049 different permutations. Final thoughts. While these are some of the combinatorics formulas, there are many, many others. All of it ultimately goes back to the addition and multiplication properties. And honestly, I would say knowing the addition and multiplication properties are probably the most important aspect of all of it. Because then you can just always go back and say, all right, well, how many do I have? How many am I going to have when I pull the second thing? And so on. All of these other formulas, they're just based on the addition and multiplication property. We see counting in many places, but for us, we will use it to measure uncertainty. And that's where we get into the idea of probability. Probability is all about measuring uncertainty. And in order to measure uncertainty, we need to be able to count different outcomes. And that counting is all of this combinatoric stuff. With that, I'll let you get to work exploring where you find counting in the real world. Good luck, folks.